Welcome back everyone. In this lecture, we will consider finite dimensional standard cyclic irreducible modules and then observe something about the highest weight. So, let us recall what we did earlier. So, for lambda in H star, we define the V of lambda to be the quotient of Verma module Z of lambda modulo M of lambda. So, where Z of lambda is the Verma module, Z of lambda is defined to be take UG and then take left ideal generated by the following elements H minus lambda of H 1 where H comes from H and then X where X comes from N plus. So, now what is M of lambda? M of lambda is the sum of all proper submodules, the sum of proper G submodules of Z lambda, and we observe that this is the unique maximal G submodule. So, maximal always means it is proper, okay, we do not need to tell it is proper. So, then V of lambda is defined to be the unique quotient, the irreducible quotient of V lambda. So, this is the unique irreducible quotient of Z of lambda. So, then now, we make following observations. So, because Z of lambda has some important properties, one can immediately see that those properties can be carried to this V lambda, because it is easy to see that quotient of any standard cyclic module is again standard cyclic module. So, in particularly V of lambda must be standard cyclic module. So, first observation, this is V of lambda is standard cyclic module and this is also irreducible. Okay. And of course, it is generated by lambda. So, V of lambda is indeed generated by U n minus V lambda. So, now this is also span of some y beta 1 power r 1 etcetera y beta n power r n. So, we call this quotient also V lambda, there is no confusion. Okay. V lambda again is defined to be the cyclic generator. Okay. So, cyclic generator of V lambda. Again we use the same notation for Z of lambda and there should not be any confusion. Okay. So, for R1 etcetera Rn being non-negative integers. So, now this tells you that the weight of V lambda, this is indeed contained in lambda minus q plus. So, that is the most important thing, and if we take any weight space, okay, if we take any weight space, so that should have finite dimension for all weights of V lambda. So, these are all some important properties that we have for standard cyclic modules. So, those properties should continue to hold here. Since V of lambda to begin with irreducible, so the maximal module that is contained in V lambda will be 0, okay, which is the proper unique module. So, now so we make further observations for these modules if they are when they are finite dimensional. Okay. So, let us start with V lambda, okay, start with lambda in H star and assume that suppose V lambda is finite dimensional module. Okay. So, basically it is a standard cyclic module, irreducible cyclic module and then which is also finite dimensional. Okay. This is the assumption that we have. Then we want to conclude something about the lambdas and the weights of V lambda and so on. The very first thing that we observe is that the lambda must be dominant. Okay. These are all the observation. So, observation 1, lambda must be dominant, which is same as saying lambda of hi is in z plus for all I from 1 to n. Okay. So, how do we prove this? The proof of this again follows from SL2 theory. So, for I in 1 to n, let us look at this copy of Si. So, the copy of SL2 inside G, which is defined to be Si. So, which is nothing but the subalgebra generated by Xi Yi inside G, which is isomorphic to SL2. This we know already. So, now what we do, we take this USI module generated by V lambda, which is inside V lambda. So, note that this is again SI module. So, now we are taking SI submodule generated by this V lambda, the highest weight vector. So, note that V lambda we can also call it as highest weight vector, because it has weight lambda and x kills all those V lambda, okay, because x V lambda is 0 for all x in n plus, and h V lambda is lambda of h V lambda. So, now what we know about this module? So, that is the important observation. Note that this is first of all finite dimensional. So, this is actually finite dimensional SI module. So, now look at its actually the spanning set. It is not hard to prove this is indeed span of V lambda, y I V lambda and so on, y I power some s V lambda. Now, note that h I V lambda is given by lambda of h I V lambda and x I V lambda is 0. That means, this V lambda is indeed maximal vector in the sense of SL2 module. Okay. So, but we have already proved something. If you take a maximal vector and then generated module out of it in the finite dimensional representation of SL2, it must be irreducible module and it is isomorphic to that irreducible module corresponding to the lambda of Hi. So, this is naturally isomorphic to V of lambda of Hi. This is something we already proved. So, using this observation we can see that this S must be lambda of Hi. So, then from this we can conclude that lambda of Hi must be non-negative integer, because that is being the maximal eigenvalue of Hi, okay, inside this irreducible module. And we can also see that this yi power lambda Hi plus 1 V lambda, that should be 0, and I is chosen to be some integer from 1 to n. So, and this is these two observations must be true for all I. Okay. So, in particularly this holds for all I 1 to n inside our module V lambda. Okay. So, if you take our V lambda to be finite dimensional, then we observe that lambda must be dominant, that is the first observation. The second observation that we made, this y I power lambda Hi plus 1 V lambda is 0, second observation. Now, look at the while group element action, okay, the while group action, which is Sn plus 1 on this weights of V lambda. So, recall, if you take finite dimensional irreducible module of Sn plus 1, we proved that the while group Sn plus 1 acts on the weights of that, and it also actually preserves the dimension of the weight spaces. Okay, this is something we already proved. So, we have to prove something similar here in this setting as well, okay, because this we are considering the abstract module. So, that is the observation 3. So, in this again we use the same proof using the SL2 theory proof. So, now start with some weight of this V lambda. Okay. So, then consider this USI module generated by V mu. Then look at this SL2 submodule or SI submodule again generated by V mu, which is inside V lambda, and this is also SI module. Okay. So, now what we can say about this module V dash? Okay. Observe this weights of V dash. Okay. The weights of V dash must be contained in mu plus m alpha I, where m comes from integers. So, this can be proved using the PBW type basis of USI. So, note that USI being SI being isomorphic to SL2 and SI being 3-dimensional space, this is indeed spanned by. So, CXI, okay, let us use this CYI, CHI and then CXI. So, this is the basis for this 3-dimensional subalgebra SI. Then if you look at USI using the PBW theorem, we observe that this is indeed span of yi power something, let us call it R1, and then hi power something R2, and then xi power something R3, where R1, R2, R3 they are all non-negative integers. Okay. So, then this tells you that from this PBW type basis of USI module generated by V mu, this is again obtained by span of. So, you take this typical PBW type basis element and then apply it on this V mu, then we get the spanning set. Okay. So, now it is not hard to see, since the weight of this is mu. So, the weight of this vector is going to be, so I will leave it as exercise, this is something we have checked already. The weight of this yi R1, okay, hi R2, xi R3 V mu, if it is non-zero, so then that is going to be exactly mu minus R3 alpha I, this h is not going to add anything, that is R2 times 0 minus, sorry, this is mu plus, because this corresponds to alpha I, this corresponds to 0, this corresponds to minus alpha I. So, you will get R3 alpha I plus R2 0 and then minus R1 alpha I. So, basically what it says that if you take this element yi R1, hi R2, xi R3 V mu, so this is going to lie inside. So, you look at this weight space of this USI of V mu. So, then this is going to be exactly mu plus R3 minus R1 alpha I. Okay. So, this will be the h weight, not even like we are computing hi weight, we are computing the h weight, and we are saying that the h weight of V dash will be contained in this mu plus m alpha I, where m running over integers. Okay. So, in particularly what will happen to the h weight? So, the weight of V dash is contained in the translation of this mu plus z alpha I. So, if I compute, for example, the typical mu plus m alpha I and then compute the hi eigenvalue, then that you have just evaluated hi, then this is going to give you mu of hi plus twice m. Now, for various m, this mu of hi plus 2m, they are all distinct. That forces that the weight spaces of this, okay, so they all like, so the weights of this are all distinct for various m. So, but this is going to be finite dimensional module, SL2 module. So, in particularly we know that the hi eigenvalues of this V dash module will be symmetric. Okay. So, this is, so now I am looking at the HI weight. If I look at weight HI of V dash, we know that this is same as minus weight HI of V dash. As a SL2 representation, if you consider HI weights, which is HI eigenvalues, there is a symmetric for any finite dimensional representation. So, for V dash also we have the symmetry. So, now that tells you that, so for example, if m equal to 0, you are getting mu of HI. So, which is going to be the weight of V dash with respect to HI. So, then that forces that minus mu of HI also must be a weight of this V dash. So, but what will corresponds to minus mu of HI among this mu of HI plus 2m, and it is not hard to see that this is equal to minus mu of HI will imply that m equal to minus mu of HI. Okay, sorry, minus mu of H. So, now if you think in terms of this H weight, what it should correspond to, mu plus m alpha I if you take, and then what should be that. So, that is nothing but mu minus mu of HI alpha I. So, that is your corresponding weight. So, this is what corresponds to minus mu HI when you evaluate at HI. Okay. So, that means this should be there inside the weight of V dash, because for all other values of m you will not achieve this, you will achieve only for this value m equal to mu of HI. So, it must be there inside. So, that means this is there inside your V of weight of V lambda. So, this analysis indeed says that whenever mu is weight of V lambda, then that implies SI of mu, which is mu minus mu HI alpha I, is indeed weight of V lambda. So, this actually tells Sn plus 1 acts on this weight of V lambda. Okay. So, that is something very clear. So, not only that, again using SL2 representation theory, we observe that whenever you have k as weight of this V dash, then minus k is going to be weight of this V dash. Not only that, the dimension of V dash k is same as the dimension of V dash minus k. So, this is true for all finite dimensional representation of SL2. So, in particular it is true for V dash. But again, using the similar analysis, you can see that, so this space must be what? So, if I take k to be mu of HI, so mu of HI can be both positive and negative. Okay, it's not necessarily positive. This is just an integer, but for any integer we know that whenever k is there, minus k is there, and then Vk dash dimension should match with V minus k dash. So, since this holds for SL2 representation, you can easily see that for k equal to mu of HI, we have the dimension of Vk dash is same as dimension of V mu, okay. So, which is equal to dimension of V minus k dash, which is same as the dimension of V SI of mu, okay. So, this things holds inside V dash. So, in particularly, not only that Sn plus 1 acts on the weight of V lambda, and the action actually preserves the weight multiplicities. So, in particularly dimension of V mu is same as dimension of V sigma mu for all sigma in Sn plus 1. That is because it is true for any Si, and Si actually generates this Sn plus 1 for 1 to n. Okay. So, that is why this is true for all weights of V lambda. So, these observations that one can make immediately for finite dimensional standard cyclic irreducible module. We already made this observation for finite dimensional irreducible representation, similar observation that we are making it here. So, now you can actually conclude the following, okay. In actually somewhat more stronger version is true, but I will actually leave it as exercise because it is more combinatorial result. But what one can observe immediately, so observation 4. So, if I take the weights of V lambda, okay. So, we already told that Sn plus 1 is going to act on this weights of V lambda. But can we say using that anything about the weights of V lambda? One can immediately say that this is going to be a subset of all the orbits of dominant weights which are below lambda. So, you take the orbit Sn plus 1 acting on mu, where mu must be smaller than lambda and then mu is also dominant. So, if I take all possible orbits, okay, so basically what is Sn plus 1 dot mu, this is sigma mu where sigma comes from Sn plus 1. Okay. So, I am actually taking all possible orbits of this mu, where mu is smaller than lambda with respect to the dominance order and mu comes from the dominant weight. Okay. So, note that, so this is indeed finite set. Okay. So, let us actually prove that in as a separate note. Okay. Here is the lemma, so which will be used later. Okay. So, this lemma actually tells something about this set. So, this set is indeed finite. So, that is what this lemma says. Okay. So, if I take this disjoint union Sn plus 1 dot mu, mu is less than lambda, mu is comes from lambda plus. So, this is a finite set. Okay. So, how do you actually see this? So, note that the each orbit is a finite set because Sn plus 1 is a finite group. It has n plus 1 factorial elements. So, each one of these orbits, so they are all finite. So, once we prove that the number of dominant weights that lies below lambda, that is finite, then that would imply that this set is finite. First of all, I want to actually emphasize that, so this is also indeed disjoint union of orbits. So, because there will not be any intersection between these two orbits. Okay. So, these observations let us make and then prove it, because these things will be used later. So, this is indeed disjoint union of orbits. So, that means if you take two dominant weights which lie below lambda, so then they can't be in the same orbit. Okay. So, that is equivalent to saying that this is indeed disjoint union of orbits. So, let us prove one by one. Okay. First, what I want to say, if I start with any mu inside lambda, okay, we can only focus on weights, okay, coming from this lambda. Okay. Then I can actually say that there exist W in W. Okay. So, W is Sn plus 1 such that W mu is indeed dominant. Okay. This is the first thing. So, this is actually a very simple exercise. You think in terms of the epsilon I basis. You take mu to be A1 epsilon 1 plus etcetera plus An plus 1 epsilon n plus 1. Note that, okay. So, this is dominant if and only if these AIs are in the decreasing order. So, that is actually A1 greater than or equal to etcetera greater than or equal to AN plus 1. So, this is actually already we know. So, now if I start with some mu, okay, let us start with some mu, say mu equal to A1 epsilon 1 plus etcetera AN plus 1 epsilon n plus 1. So, these AIs may not be in the correct order. So, these AIs may not be in the correct order. Okay. So, then how do you make it in the correct order? Of course, you can choose a permutation and then permute these AIs and then write it in the decreasing order. Okay. So, choose W in Sn plus 1 such that A W inverse of 1 is greater than or equal to A W inverse of n plus 1. So, then it is clear that W mu is nothing but A W inverse of 1 epsilon 1 plus etcetera A W inverse of n plus 1 epsilon n plus 1, which is dominant. Okay. So, this is indeed easy observation. So, now what is the second observation? Suppose mu and mu dash both are dominant and mu dash is inside the orbit of mu, okay, then that would force that mu equal to mu dash. Okay. Indeed, we will prove something stronger. Suppose if you write mu dash equal to W mu, then that would imply that W equal to identity. And in particular, we have mu equal to mu dash. So, why this is true? Okay, let us write mu as some A1 epsilon 1 plus etcetera plus AN plus 1 epsilon n plus 1. Similarly, write mu dash to be B1 epsilon 1 plus etcetera plus Bn plus 1 epsilon n plus 1. Because both of them are dominant or elements of lambda dash, lambda plus, then that would force that A1 is greater than or equal to etcetera greater than or equal to An plus 1. And similarly, B1 is greater than or equal to etcetera greater than or equal to Bn plus 1. So, now if you take W and then permute, for example, AIs, then what will happen? If you take W mu, so that is going to be A W inverse of 1 epsilon 1 plus etcetera plus A W inverse of n plus 1 epsilon n plus 1. So, you are permuting the AIs and you are claiming that still you are getting the decreasing sequence. Okay. That is not possible unless W is identity. Okay. Then this is you are saying that mu dash and you are saying that W inverse of 1 is again greater than or equal to A W inverse of n plus 1. And of course, so here you are actually kind of saying that, okay. So, one has to be little bit careful in this argument. So, for example, all the coefficients are equal. So, then you will be able to actually say that this W is indeed like can be taken to be any element of Sn plus 1 and then it acts on that trivially. Okay. So, it fixes that, so that you are going to still get this the permutation of that, which is actually kind of satisfying this property. So, to avoid that triviality, maybe I will not claim this W being identity. Okay. But it is actually not hard to see even without this claim. Okay, one can get what we wanted as long as your mu dash is inside the orbit of mu. So, then and mu and mu dash both of them are dominant, then that will force that mu equal to mu dash. Okay. So, I will actually kind of leave it to you to think about it unless okay, the coefficients of okay. So, when you are actually trying to permute Okay. So, if ai, aj, if they are not equal, then when you are actually permute them, if ai is greater than aj, then the order is going to change. Okay. So, up to that kind of w's, okay, so only you will be able to act it on mu, and then you can get another dominant weight. Okay. So, that will force that. So, because this is true, so this will force that mu dash is same as mu. Okay. So, I will leave it to you to convince yourself that there could be some non-trivial w's, still it can be dominant, there is no other option, because this is being dominant. So, it has to be in the decreasing order, and a1 etc. an plus 1 to begin with in the decreasing order. So, by permuting it, you are again getting the decreasing order sequence. So, that will force that. So, this is same as a1 and this is same as an plus 1. Okay. So, that is something like you can think about it very carefully. So, now this indeed proves that if I start with some weight, okay, let us say below lambda. So, start a weight which is below lambda, then there exists w in Sn plus 1 such that w mu being dominant. So, that means if I take this set of all weights, okay, set of all mu in capital lambda such that mu less than lambda. If I look at this set, then this set can be written as union of the orbit Sn plus 1 mu, where mu is less than lambda and then mu comes from dominant. Okay, this is obvious. So, now if you look at two different orbits for different mu's, okay, so then they cannot intersect, that is what the our previous observation says. So, that means this must be disjoint union. So, now why this set is finite? So, it is enough to prove that, okay, to prove this set is finite, it is enough to prove the mu lambda. So, mu is in lambda plus such that mu less than lambda, this is a finite set. Okay. And that can be actually obtained very easily. So, look at what is the meaning of lambda greater than mu. So, that means lambda minus mu is summation k I alpha I, where I range from 1 to n, where k i's are all in z plus. Note that alpha I is nothing but epsilon I minus epsilon I plus 1 for I from 1 to n. So, now you write lambda in terms of the epsilon I basis, a1 epsilon 1 plus etcetera an plus 1 epsilon n plus 1, and then write mu as again b1 epsilon 1 plus etcetera plus bn plus 1 epsilon n plus 1. Note that a1 should be greater than or equal to an plus 1 being dominant, b1 should be greater than or equal to bn plus 1. Now, let us do this calculation. Look at lambda inner product with lambda minus mu. So, this is going to be lambda comma summation k I alpha I range from 1 to n. Then if you take it out, summation lambda alpha I, where k comes out, where I range from 1 to n. Now, note that lambda alpha I is going to be lambda epsilon I minus epsilon I plus 1. So, this is exactly a I minus a I plus 1, which is non-negative number. So, then that means this summation must be non-negative number. So, similarly, you can see that mu comma lambda minus mu again non-negative number, again mu being dominant. So, this force that lambda is bigger than lambda mu, which is bigger than mu, okay, because lambda mu is same as mu lambda. So, that tells you that lambda must be greater than or equal to mu. Okay. So, it is indeed telling you that when for those dominant weights mu in lambda plus, mu less than lambda is contained in mu coming from capital lambda such that mu is smaller than lambda lambda. Okay. So, because we are actually, if we take the real span of this alpha i's, and then because this capital lambda sits inside the real span of alpha I, okay, or you can also work in the real span of epsilon i's. So, there you can see that using the standard inner product, so this becomes inner product space. So, it is a Euclidean space, and this inner product is actually the standard inner product. So, basically you are saying that you are looking at the lattice elements which are bounded above by some particular norm. So, lambda is fixed, okay, it is a norm lambda square, that is what on the right side. So, you are looking at the integral points that are actually bounded above, the norm is bounded above by some constant, and that must be finite using this Euclidean geometry. So, that forces that this set is finite. Okay. And one can actually give different proof using by looking at the coefficients of alpha I and so on. So, I will leave you to think about it actually. So, the choices of this ki's, the choices of this bi's only will be finite, okay, because mu being dominant and mu is less than lambda will force that, since these ai's are all fixed, okay, in terms of ai's you can actually get some bound for the bi's, and that will tell you that the choices of b1 etc. bn plus 1 will be only finite. So, this way you can conclude that the number of dominant weights which are smaller than lambda must be finite, and that is telling you that this entire union is finite, which tells you that those weights which are actually smaller than lambda, so that set is already finite for lambda dominant. Okay. So, we will use this later in order to actually prove that if lambda is dominant, then V of lambda must be finite dimensional. Even though we define this V of lambda in a more abstract way as a quotient of this universal standard cyclic module, which is Verma module. So, for dominant lambdas, we can always get finite dimensional irreducible representation. So, that will be our ultimate result. We will actually see the proof in the next class. I will stop here. Thank you.